This sketch animation video tutorial will help you get through the circular motion video assignment. It covers the principles and formulas first and then gives you a solved example with real mathematical values. It goes by fast, so hit the pause button often when you need to. There's one math mistake in the video and I'll give 5 bonus points to the first 5 students who find it and report it to me via email. When we did the linear motion unit, we looked at a bunch of physical quantities such as time, which we call t, position, which we call x or y, distance, which we call s or d, displacement, which was a vector x, speed, which was a scalar s, velocity, which was a vector v, and acceleration, which was a. As it turns out, these same linear quantities also apply to our unit of circular motion, and they use the same units that you see right here. So we can go ahead and check these off, and we'll be using some of these in our video assignment. We're going to talk about a certain kind of circular motion called uniform circular motion, in which the speed is constant. The velocity is not constant, it changes direction, but the speed is constant. There are many examples of uniform circular motion, such as a ball spinning around a string, or maybe a bug on a spinning vinyl record, a Ferris wheel at an amusement park, or maybe the Gravitron ride at the amusement park, which is a ride that spins really fast and then the floor drops out, but you don't fall down because you're stuck against the wall, kind of like a centrifuge. And finally, even the Earth rotating around the sun is like a big macro scale circular motion problem. First quantity we'll talk about in circular motion is time in seconds. The time it takes to go around one time is called the period, and it's measured in seconds. It's called period because it's recurring, which means that it repeats over and over as a rotating object reaches its starting point and then continues around again. Yeah, the period is related. You probably remember the period because it's related to a quantity we studied in the sound and waves unit, frequency. Period is basically, as we said before, the number of seconds it takes to complete each cycle or rotation around the circle. So period is seconds per cycle of rotation, okay? And frequency is the number of rotations or cycles per second. So yeah, period and frequency, they are inverses of each other, and they're kind of like mirror images. If you find one and you want to find the other, just do 1 divided by it and you'll find the other quantity. Now, as an example, let's say our spinning ball on the end of the rope goes around once and takes 4 seconds to make one complete rotation or cycle. The period t would be 4 seconds. The frequency would be 1 over 4. Remember, it's the inverse. So it'd be 1 over 4, one cycle for every 4 rotations. One cycle for every 4 seconds that pass. So it'd be 0.25, 1/4 being 0.25 rotations per second. If you think about a ball taking 4 seconds to spin around, I think you'll agree that that is pretty slow. Totally slow, in fact. Now let's talk about position and distance. The ball is rotating around an axis of rotation on the string of length L. That is really just the radius of the circle, which has a distance around which we call circumference that is equal to, remember the formula from math? C equals 2 pi r. This should be a review for you. So let's say that the ball on the end of the string goes around a quarter turn, okay? Only 1/4 of a turn. So what we're going to do is we're going to multiply the circumference that we found by 1/4. That will tell us how far the ball moved around a quarter turn of the circle. If we assume that the ball is on the end of a string that is a meter long, then the radius of the circle is 1 and the distance traveled is pi over 2 meters. If the ball moves half a turn around the circle, then we multiply the circumference by 1/2. The distance traveled by the ball is then pi meters. This is if we leave things in terms of pi. So pi over 2 compared to pi. Let's talk about velocity now. The ball is moving around a circle, so we might think the velocity is also curved. But if we think about the ball's velocity at one particular moment in time, we can see that it faces in a specific straight line direction. North, south, east, and west is what we can see right here. Now you need to realize that while the speed is constant, in other words, the size of the arrows is the same, the velocity is not constant. It's a vector and the direction of the arrows keep changing. Now why do we call it tangential velocity? The descriptor comes from the fact that a line that intersects a circle at one point in geometry is called the tangent. If you're having a hard time visualizing the tangential velocity, here's an example of a guy doing a hammer throw. Okay, he spins around and launches a hammer as far as he can. The question is, if he wants to release the hammer so that it flies off the top of the page, at what point in the circle should he release it from? Well, not at the top. If he did that, the hammer would fly off to the left. He should release it a quarter circle before the top. This is because the hammer will fly away tangent to the circle. So it will not go straight off to the right, it will go upwards. Now there's a question in the assignment about what water does when it flies off a wet spinning object. I'm going to give you an example of a bike wheel going through a puddle. This clearly shows what happens to the water droplets that stick to it. If the bike wheel did not have a splash guard, as I'm sure you've had the experience before riding in the rain, it would be all up in there. Just go ahead and check it out. Now let's talk about how velocity is related to how far an object is from the axis or center of rotation. In other words, how is r, the radius of rotation, related to the velocity with which the object spins around the circle? Here we see two bugs on a spinning platter, one which is twice as far away from the center as the other. So we see that one is a distance of r from the center, and the other one is a distance of 2r from the center. So which bug is spinning faster? That's kind of a loaded question. In one sense, they are both moving the same number of rotations per second and have the same angular velocity. But in another sense, the outer bug is covering more distance, meters or centimeters, than the inner bug in the same amount of time and has therefore a greater tangential velocity. It's kind of like two sprinters running on a track. You have a sprinter on an outer lane of a track and another sprinter on an inner lane of the track. Who would you want to be? The sprinter on the outside lane covers more distance than the sprinter running on the inside lane in the same amount of time. Since circumference is determined by radius, a smaller radius means a smaller circumference and less distance that has to be run. However, both runners or bugs have the same angular velocity, meaning that they are both doing the same number of rotations or fractions of rotation around the circle. So they'll both do a complete trip around the circle in the same time, although the outer runner will end up running more distance in meters or centimeters. So really all that we're saying is that tangential velocity is directly proportional to the radius of rotation. The bigger the radius, the bigger the tangential velocity. Ergo, the smaller the radius, the smaller the tangential velocity. And yes, if the radius is twice as big, for example, than the tangential velocity, then the tangential velocity will also be twice as large. If you double the radius, you're also doubling the circumference. Now, we use a symbol to represent proportionality, which you'll see here in a second. It's a Greek letter. So here what we're saying is that a small distance or radius A corresponds to a small circumference and a big distance corresponds to a big radius. That's a proportionality symbol. So VT is proportional to the radius. So let's calculate our tangential velocity now. Velocity is just distance over time, and circular distance is the circumference over time. And time is the period, the time in seconds to make one complete turn around the circle. So tangential velocity is 2 pi r over capital T, the period. So hopefully you can see how this formula for tangential velocity is really just an old friend. It's the velocity in disguise. In this case, it's really just the circular distance divided by the time in seconds. Let's try to understand centripetal acceleration now. This is called A sub c. Most people have a rough time understanding that you are accelerating towards the center when you are in a spinning object. It feels you are being pushed out, not in, if anything. But is that a force pushing you outward, or is that just your inertia, your body's mass trying not to change its location, which keeps moving? It turns out it is inertia. Here are 3 examples that show you there's a center-seeking force, and so the acceleration that goes with it is also center-seeking. The first example will be the Earth spinning around the sun. The Earth is moving around tangentially at a velocity v sub t. However, the sun is pulling on the Earth with a gravitational force equal to a sub g. So that's a center-seeking force. Let's talk about a pendulum swinging back and forth. A pendulum, the bob of the pendulum has a weight pointing downward, which is called F of g, but the pendulum is not going downward, so there must be an upward force, the force of tension in the rope, pulling it toward the center. Finally, let's think about you having superpowers, being super strong, and just for fun, you're throwing around your friends in a horizontal surface. They think it's kind of fun. So you think about yourself, what are you feeling? Well, you're feeling that you have to pull towards the center, otherwise your friend would fly off and it might not be too fun for them. So that F of P, that force of pull, is definitely a center-seeking force. Let's now do a household item, and like your video assignment calls for, and go through all the calculations needed. Let's use a simple spinning top and measure its radius in centimeters first. Let's get out a ruler, and won't be perfect, but we find that this particular spinning top has a radius that is equal to 3.5 centimeters. So if we want to find the distance around the top, that will be the circumference. We multiply the radius by 2 pi. We get c equals 2 pi r, and that gives us 7 pi centimeters. That's if we leave our answer in terms of pi. Now we have the total distance traveled by a spot on the edge of the top. Now we can find out how many times that top will spin every second. So if you guys remember what that's called from our sound and waves unit, cycles or rotations per second, that is called the frequency. Now, you can find the number of spins per second by estimating or just counting visually. You might be moving pretty fast, so that might be kind of hard. So you might want to get your slow motion app on your camera out to get a more accurate picture of the cycles per second. So you probably want to do it over 5 to 10 seconds instead of just 1 second, because it's really hard to time or see things in 1 second. We're going to assume a constant rate of rotation of our object to keep things really simple. Let's say the top spins 20 times in 10 seconds in our particular case. What we're going to do is we're going to multiply that 20 by the distance around 1 time, in other words, the circumference, and then we'll have the total distance traveled by a point on the rim of the top. So we got 20 times 7 pi, and that will give us the entire distance that that point moved in those 10 seconds. That gives you 140 pi. So if we want to find the tangential velocity, it was 2 pi r divided by t. So we're going to multiply that 140 pi, divide that 140 pi by the 10 seconds. The zeros will cancel out nicely, and that leaves us 4 pi centimeters per second. That is our tangential velocity. So just to put this in perspective, this would be like that point on the rim of the spinning top. If we laid out the circumference in a straight line, that point would have traveled 14 pi centimeters, which is 43.9 centimeters in a straight line in 1 second. Just to put it into perspective. Okay. Now let's find the centripetal acceleration of that point on the rim of the top. The center seeking acceleration of that point is given by the formula a sub c equals vt squared divided by the radius r. Okay, that's the tangential velocity right there, and the center seeking acceleration, drawing with a blue arrow pointing towards the center. Again, that formula is AC equals VT squared over R, plugging in our tangential velocity and dividing by our radius. Let's get our handy dandy calculator out and find out what the answer is. Drum roll, 552.7 centimeters per second squared. Now summarizing what we found. Let's put Humpty Dumpty back together again. It's all the stuff that we've done in this video. We've broken Humpty Dumpty into little pieces, and now it's time to patch the fella up. So he's got some pretty big old shoes here. Maybe that'll stop him from breaking the next time he goes down. We have found a spinning top, or used a spinning top, identified an axis of rotation, identified the radius as 3.5 centimeters by measuring, then found the circumference by multiplying by 2 pi r. The period was 10 times, or 10 rotations in 20 seconds, gave us 0.5 seconds per rotation. The frequency is just the inverse of that, so you get 2 rotations per cycle. The tangential velocity of 14 pi, and centripetal acceleration of 552.7 centimeters per second squared. Ta-da!